These ones are a little tricky, that's why I'm doing the exact questions that are in your homework. We probably won't cover the sandwich theorem too much, but it is typically covered in a calculus course. What the sandwich theorem says is if you've got three functions, where one is sandwiched in between two other functions on some interval, meaning it doesn't have to be over every possible value for x, but maybe on the interval -1 to 1, maybe this is true, that f of x is always less than g of x, and g of x is always less than h of x. Okay, so this function is bigger than this function. This function is smaller than this function. If that's true, and if the limit as x approaches some number, we'll call it c, and then we'll say that as x gets closer to some number is some number, the limit as x approaches some number equals d. And then if you do that for f of x, the smaller function, then you've sandwiched it. And then you don't have to do any calculus. You can just say the limit as x approaches c of g of x is also d. Because the limit was the same for the function that's bigger and for the function that was smaller. If they're both d, then we can assume that g of x also has the same limit. That's a rough sketch of the sandwich theorem, okay? But we're going to use this inequality to help us solve this problem. We need to find out, you could do this, you could find the limit graphically, really easy. Plug that into your graph like we saw in previous problems, and then evaluate the limit as x approaches infinity. Okay, but to do this problem, we'll start with the fact that we have learned about sine and cosine before. Sine and cosine, if you don't have any other numbers attached to them, are always between -1 and +1. You could replace this with sine of x. They're always between -1 and +1. Okay, but we're not dealing with just cosine of x. We're dealing with 1 minus cosine of x. So let's see, how can we fix that? I can multiply everything in this inequality by -1, right? So that's just going to flip everything around. If you multiply by a -1, then you have to switch the inequality symbols. But then I can rewrite it like this. This is -1 is less than or equal to negative cosine of x. We're kind of back to where we started. We just have a negative sign like we wanted. Okay, so I'm trying to construct this by doing operations to this compound inequality. I multiplied everything by -1, and I got this when I rearranged. Now I'm going to add 1 to this side, and this side to keep it balanced. So -1 plus 1 is 0. And then I added the 1 in here, so that's a +1. And then 1 plus 1 makes 2. And I still need an x squared in the denominator. I'm close to reconstructing this whole thing. I need an x squared in the denominator, so I'm going to divide everything by x squared. So 0 divided by x squared is 0. All this stuff divided by x squared is the rational expression we wanted in the first place. Okay, so we've got all the pieces we need for the sandwich theorem. If we let f of x be 0, and if we let h of x be this 2 over x squared, then the limit, then we just need to consider the limit of each of them, and then we can say that this limit would also agree. We need to consider the limit as x approaches infinity for 0. So what's the limit as x approaches positive infinity for 0? And there's no x to even deal with, right? It's just a constant 0. The limit as x approaches infinity for this h of x, for 2 over x squared. Now this is one that's going to come up a lot. When you have x in the denominator and no x in the numerator. The limit as x approaches infinity. Think about what's happening to the y values. If you plug in a billion squared is even bigger. 2 divided by a huge number is getting infinitely close to 0. So the limit for our smaller function is 0. The limit for our larger function is 0. That means the limit for g of x we can say is also 0 by the sandwich theorem. Let me do one more. If we have the limit as x approaches negative infinity of sine of x over x, we want to do the same thing. We want to reconstruct something so that we can evaluate the limit using the sandwich theorem. We want a smaller and a larger function, and that's where we start with this fact that -1 is always less than or equal to sine of x. which is always less than or equal to x. 1. Sorry, whoa, big mistake there. Look, if you graph sine of x, the y values always are between -1 and +1 inclusive. Okay, that's a fact about sine and cosine. If you don't mess with them, if you just graph sine of x, the y values fluctuate between -1 and +1. So we want to reconstruct this, not just sine of x. So let's divide everything by x. And now we've got our two functions that we want for the sandwich theorem. This is the function that's always smaller. This is the function that's always larger. And so we can evaluate the limit as x approaches -infinity for this smaller function. And think about what's going on here. A -1 divided by -1 billion is really close to 0. And then the limit as x approaches +infinity of 1 over x. Negative infinity. That's also going to be 0. It's going to be like you get -0.0001 as you plug in approximations, but that's infinitely close to 0. So by the sandwich theorem, since these two limits as x approaches -infinity are 0, by the sandwich theorem we can say this limit is also 0.